Well, thank you for staying this late. We're the last technical talk of the afternoon. My name's Ric Wheeler. I manage the kernel file and storage team at Red Hat, which is not the Red Hat storage team. That's the user space cluster stuff. So here we're going to talk about the kernel and the kernel file systems and storage stack.
I'm Steve Dickson. I'm technical lead of the NFS. I'm not really sure what that means. I think it's just when the bus comes by, they throw me under it.
That's right.
I think that's what that technical means. But what's that? Yeah.
See, it means Steve is too smart to actually be a real manager. He's
yeah, exactly.
The fun stuff. Yeah, so we're going to get started, and I do welcome questions. So if there's a question as we go, jump up. We have a mic in front. Steve can run it up to you. Unless he's talking, then I'll run. So again, we're going to start with an overview of where we are in RHEL 6. How many people here use RHEL 4 still? Okay. I'm not going to mention RHEL 4. RHEL 5. Not going to talk about RHEL 5 much. So we're going to start mostly on RHEL 6, what we've been doing recently. A little bit of background and going in towards RHEL 7 and even post RHEL 7, what we're working on in the upstream community. So hopefully it'll be interesting. So a couple of major things we did in RHEL 6. Number one is we've worked really hard on LVM scalability. If you use LVM, traditionally, it wasn't very high performance if you did more than one snapshot. So we'll talk a little bit about that in detail. In RHEL 6, we also continued to give you more options in file systems and worked on performance as always. And actually, we're happy to announce we were the first in industry to support the new version of NFS on the client side called Parallel NFS or PNFS. There's actually a panel tomorrow afternoon where we have a lot of industry leaders who will be talking about that in detail. So starting at the bottom of the stack, LVM is the logical volume manager. It's built on something called device mapper in the kernel. What we did with the LVM redesign is traditionally you have to have a separate exception store for each thing you want to snapshot. With the new design, you can have a shared exception store. This mechanism itself is much more scalable. It's also more convenient to set up and administer. You don't have to do a partition per target. Building on this shared exception store, we do something called thin provisioning. It's actually an old enterprise array feature. If you've talked to vendors like NetApp, IBM, EMC, and so on, they've been allowing you to do this for a long time. You can now do this with a device mapper target, which is kind of cool. Because if you can lie to your users, tell them each they've got a terabyte file system and only give them 100 gig, you don't have to worry about resizing file systems that much. The device mapper LVM stack will take care of that for you, which is very nice. You would still have to grow it if you fill up the terabyte, the virtual terabyte, and go to 2 terabytes. But shrinking, it only uses the space that you actually use in the file system itself. So I'm not great with diagrams. I stole this from John, who's still lurking in the back, product management guy. But if you see here just how you carve up your disk today, when you wanted to set up exception stores, you had to pre-allocate the partitions. Clearly, it's very wasteful. What if someone doesn't really use a lot of snapshots and somebody else uses a lot? You can't actually share that space. With a shared exception store, whoever uses it gets it. And if you don't use it, it's just one pool of storage that you can allocate. The other thing that's kind of nice about this, in RHEL 6.0, we actually added support for something called discard. Discard passes down from the file system stack. Every time you delete a file, truncate a file, it tells the storage underneath it, hey, this isn't any longer in use. This information actually forks out into things like SSD trims commands. It lets the SSD device do wear leveling. For thinly provisioned storage, including device mapper's DM thin P target, it lets it know that it can give that space to somebody else. So that works in RHEL 6. Device mapper thin actually takes advantage of that mechanism. Anybody use thin LUNs or virtual LUNs in production? NetApp guys have to put their hands up. Yeah. Yeah. So again, this is stuff that we've worked on pretty hard. It's nice to have a software alternative to do this as well. Again, here's another example. You could have, say, 90 gig of available space in your exception store, 10 gig physically in use, and as you grow, you just use that spot, right? You just grab that 10 gig. If you remove it, it goes back to the common pool. So you're not permanently having to give storage to one specific file system, which gives you a lot more flexibility as a system administrator. This feature is turned into a full production support feature in 6.4, and I encourage people to give it a try. Share with us how it works for you. The other feature I mentioned earlier today is we continue to add support at the LVM layer for managing software RAID devices that are implemented by the MD stack. In 6.4, we added support for RAID 10 devices. This is actually not changing the implementation so much in the kernel, more of giving you a hugely convenient way to manage those devices from one set of interfaces. The last kind of feature at the LVM space is there's a new user space daemon that caches lookup of devices. If you've ever had to really bad performance with LVM where it's rescanning and rescanning and rescanning on high LUN count boxes, that should be taken care of. That stuff should be cached. We don't have to go back and query the devices all the time. Probably won't notice if you only have a couple drives, but if you have 1,000, 2,000 LUNs, it can be a huge win for you. So I lied a little bit. Here I am going to mention RHEL 5. How many people here still use ext3? Oh, you're boring. That's boring choice. Yeah. Well, this is the RHEL 5 choice, right? It was the default file system for most of RHEL 5's lifespan. It's actually a very solid file system, but it's really slow, right? It's significantly slower than ext4, which in turn is slower than XFS when pushed really far. GFS1 was a file system we supported for shared disk storage and clustering at the beginning of RHEL 5. In the middle of RHEL 5, we did add more choice. ext4, it wasn't supported automatically, but you could make ext4 file systems, have them be fully supported. We added scalable file system as an add-on product, which gave you XFS support in RHEL. And we upgraded to the new generation of GFS technology, GFS2, in mid-RHEL 5. And that's actually been pretty popular. Another big investment we made is we enabled the Fuse support for user space file systems for some of our partners who had file systems running up in user space. Yeah, one of those partners, or someone in the ecosystem, was this little startup called Gluster, which Red Hat ended up buying. But we made them jump to RHEL 6. So what have we done in RHEL 6? Number one is XFS is a file system we actually push at large scale. We support it up to 100 terabytes today. It's always been fantastic for taking advantage of high-performance I/O. The bigger your box is, the more storage you have, the more spindles, the faster the drive is. XFS is more clearly the win. It's not always a win if you have a really slow SATA drive, say with a single CPU. And it's specifically, for a long time, XFS was really, really bad at creating lots of little files and deleting them. That was really slow. We fixed that upstream and brought that back into RHEL 6.2 when we did something called delay log support. So if you've tried XFS for a workload that didn't work for you well before, try it again in RHEL 6.2 or later and see if that's improved your performance. GFS2 team worked a lot on performance. GFS2 gives you really tight coherence in your clustered file system space. A lot of that means locking gets knocked around the cluster. So the GFS2 team worked hard on optimizing the locks and how to prevent some of the performance issues we've seen with that. And I mentioned the XFS stuff. And we added the tech preview for RHEL 6 and 6.2, I think it was, Steve. And Steve will talk more about this later. I don't want to steal his slides. RHEL 6.4, ext4 gathered one of the features that XFS has had for a long time. It's called hole punch support. This allows you to deallocate file data in the middle of the file. Think of a common use case is you have a 2 gigabyte video and you have a really nasty scene in the middle that the dog ate the cake or something. You want to cut that out and you don't want to have to copy the whole file over. Punch lets you do that. We added that to XFS, and although most people don't edit videos in their day job, KVM guest and things do effectively. When you have a virtual block device on file, it's actually a really common feature for us. So that's supported now in XFS as well as the ext4. We pull back and refresh the Btrfs tech preview. Anybody tried Btrfs in RHEL 6? Not very happy? Not too many? Yeah. It's hard to keep it up to street. Btrfs is still in active development. We're working hard to get it stable and ready. So by the time we finished the RHEL 6.4 rebase, it was, of course, stale compared to upstream. So we're still chasing that. You'll see more in RHEL 7. So one question I get a lot is, how do you actually choose a file system? We give you choice. It's kind of confusing, right? So you have XFS, you have ext4, you have Btrfs. One thing we can do is just take away choice from you. People don't like that because your data stays forever. The first thing I always advise people to do, if you haven't seen Shaq's and Larry Woodman's talk on tuning your servers, you should really check that out or check out the video of it later. but run the TuneD profile. We worked hard to get file systems optimized by tweaking the memory settings that you have to tweak that are more appropriate for big servers, disabling things like the barrier support if you have a cache with a non-volatile battery, which enterprise storage typically has. This can help your performance markedly. So first of all, run the best practices that Red Hat's put out in the TuneD profile. And again, I say a lot of people aren't actually bound by the file system performance. If the file system's not your bottleneck, don't worry about it, just use the default. We try to make sure that the defaults work well for most applications. Yeah, and if you're not waiting the file system and you do change it, you're not going to go any faster, right? So it's hard to tell. That said, take a specific workload. Red Hat Engineering worked over the past year or so with the SAS Institute to tune our local file system performance. And in this slide, smaller is better. This is total time, elapsed time. So you can see XFS was noticeably better than ext4, which is better than ext3. This is why I encourage people to jump off of ext3 to ext4 if you can, right? Again, if you're not going to migrate data, at least make your new file systems ext4 at least in RHEL 6. You'll save time. The FSCK repair time is faster as well. A lot to be gained from moving forward. Another note is ext4 and ext3 both max out at 16 terabytes. Anybody use more than 16 terabytes on RHEL? More than usual. We do get customers pushing for over 100 terabytes, which is what XFS supports today, and with qualification from our Red Hat GSS team, we do grant occasional exceptions if the workload makes sense, right? So again, there are some users with large video stores and things where we've gone up to a couple hundred terabytes. So GFS2, I mentioned performance improvements. A lot of this stuff is kind of hidden under the cover, but it's also, we stressed how you debug GFS2 performance. The G-lock debugging, this is the kind of thing that when you start thrashing locks, it's the kind of detail that helps us debug. We also added support for 4K sectors drives in GFS2 and support for trim, which is the discard support. Okay, user space file systems. This is the basis for Red Hat storage. Anybody use Red Hat storage or Gluster, other Fuse-based file systems? Fuse has this historic reputation of being a toy file system. It's not really true anymore, right? But there are specific bottlenecks in the Fuse pipe between the user space file system and the kernel that make things really slow. We've been trying to knock them off one at a time. Some of the things that you want to do is minimize the number of round trips you have to do from the user space file system down to the kernel and back again. Readdir Plus was great. It packs more into a single readdir call. Scatter Gather I/O, we give vectored I/O support across Fuse, and the Gluster team could take advantage of that. Again, it's all basically based on performance enhancements, and it has made a real positive impact on the Red Hat storage team. So I'm going to hand over to Steve.
Hello. Again, I'm Steve D. I'm the one that ignores your NFS bugs. No, I didn't. No, really. Yeah. I don't really. I'm going to talk today about what changed. NFS is the oldest technology, but one of the most used. And this year, we really have something for you guys. It's really good. The normal NFS mount, right? Go to one server, and your clients, all go through the red spot. The red is where your bottleneck is. It has been for years. V2, V3, V4, are you kidding me? Now, parallel NFS, PNFS. You mount this guy, and you get data from all these guys. It's that simple. And so it just has to be able to expand. Now, the magic is what is basically in the shared data behind the scenes, because the server has to share the data. But you have a MDS, that's who you mount. That's basically the person you mount. And then the DS is, depending on how many you have, is how many actual servers or actual pieces of hardware is how far it will scale. I always said PNFS is just a way to get NetApps and people like that to sell more servers, but no. But and it is. It's true. It actually does scale. I'll have some examples, and how the server tells the client where to go, or how the architecture is. There's three architectures. One is a file layout. And that's basically a NAS. That's what most people have here, a NAS, where you have a network between there. The next two are block and layout, it's basically, they're similar technology in the sense that the client actually has a connection to the server, to the SAN, to the actual data. And so the server says, okay, here, go over here and go get your data. And so as you will see, it actually works. Here's the new picture, where the DNS are the pink ones, and the MDS. So data server is where you actually, I'm pointing at the screen. The MDS is where you actually mount it, and then you get the data parallel. That's where the parallel comes through. I'll be talking more about this in my talk at 2:30 tomorrow. So and actually, I'm going to fly through these slides a little faster for two reasons. One, I do have a talk on NFS, and two, there's free beer after this. So we got to get going. I understand it. Believe me.
That hockey game too, right?
Oh yeah, Blackhawks. Go Blackhawks. I'm born and raised in Chicago, so I heard that. All right. You got to be a Cubs fan, of course. All right, where are we back to this? Okay, parallel 6.4. I want to have your hands to NetApps. They're the ones that made it happen. So he's sitting right down here, Andy Anderson, he's sitting right down there. His team of 3 is the reason we have support in RHEL 6.4. Thank you. Now, the way to enable it is basically, PNFS is part of, again, in my talk, I'll go through how this all works. It's part of the v4.1. And with V4, with version 4, they had minor updates. So this is what, to do it, you'll use minus V4.1. You know, maybe we should put a minus O PNFS. I don't know. You know, I mean, is that something that's a little more obvious, right? I mean, it seems to me, but who am I? And then, of course, in RHEL Next, I have block and object support, and I thought there was maybe on this. Did you change this slide? No.
I never. That's committed, Steve.
Because, you know, we'll support that if we can have hardware to do it. Because at this particular point, we don't have hardware to do it, and so we're going to be, we definitely want to. But and the code is there. It's upstream. It's in the kernel. So the code is there. But whether we have to be able to do it. Here, what bigger is better in this one. All right, the red is mounting one NFS server and getting the data. So you mount this guy and you get the data from this guy. Okay. Now, the blue, you mount this guy and you mount this guy and you get the data from both. That's the blue. Are you kidding me? It actually works. You know, I'm shocked. You know, and this, not shocked. I need 18 minutes. But this is basically I have 2 of these things. Basically showing the same thing. Basically, this shows the same thing with IOPS. This is Oracle, and this is IOPS. They're basically showing the same thing. When you get data from 2 different servers, it's a win, basically. And that's it. I'll be back though. All right.
Yeah. Thanks. Yeah, so Steve's always hard to follow, even if he works for me. Yeah. So again, RHEL 7, what are we going to bring you in RHEL 7? The usual stuff. We're always working on performance, and I'll talk a little bit about some specific challenges we have going forward and new types of hardware. Everything will be bigger as well, and there's also a lot of, anybody ever find storage hard to administer? Ever? SAN, yeah. It's confusing. We've historically done a really bad job at making Linux storage and file systems easy to use. We're working on it though. So starting at the back, at the block layer, one thing we have even today, if you get these very high speed like Micron or other PCI Express SSD cards, the Linux kernel stack can't keep up. We can't drive enough IOs per second down to the card to keep up with what they can do today. We top out at, I don't know, 200,000 to 300,000 IOs per second. These cards can do 500,000, maybe 1 million IOs per second. This is a problem. Then the problem's going to get worse. There's a group in SNIA, the Storage Networking Industry Association, that works on something called non-volatile memory that's more generic. Think of DRAM class parts that have the same cost, performance, capacity as DRAM and don't lose state. These parts can do 5 million IOs per second or more. Right? So we're already too slow for 500,000. We have these 5 million IO per second parts coming in. There's actually, by the way, for some of these future-facing things, there's links to articles at linuxweeklynews.net, which covered talks we've done on this in detail. So go to the slides will be posted. If you don't find them, find me or somebody, Steve, and we'll point you at this. But this new kind of thing called persistent memory is pushing us even further. Yeah, so what are we doing? Number one, first thing is we want to be able to make sure that people who have a mix of environments, if you have really expensive PCI cards, PCI SSD cards, and maybe some of this new technology, which is, again, the same capacity as DRAM, it's probably not enough for your whole workload. So the first thing we'll have to do is make sure that we have a good way to do block-level caching for it. We've done two things. Device Mapper has a Device Mapper DM cache that will be a tech preview item in 7.0. We've also been evaluating the project that came out of Google called Bcache that's going into the upstream kernel, hopefully the next minor kernel release. We'll look at that. They're tuned and optimized for different sized workloads. Again, it's good to have choice, just like in file systems. Different things will run better or worse. And we're going to be pounding on both of these. We kind of like DM cache because our engineering team developed it. So we're a little biased, but the Bcache is actually pretty nice too. And one nice thing about the DM cache is we do allow you to write pluggable cache management API modules, so you or a partner can actually tune to their storage. I mentioned thinly provisioned storage before at Device Mapper. One of the things we don't do very well is we don't manage the alerts properly. So we do basically like a log a dumb alert, or we rely on external monitoring. So we're debating how to propagate this stuff up to user space daemons to properly allow sysadmins to do actionable items on this. The kernel people at the Linux Storage and File System Summit all agreed that it wasn't a kernel problem, that the user space should take care of it, which is kind of a punt, but we are going to work on getting both pieces in place for our customers in RHEL 7. I don't know if the user space gathering would have a different idea. But again, user space is a great place if you actually want to send an email or something. You don't want to have a mailer in the kernel, right? So there are things you want to do. We'll continue to add more support for LVM RAID types and bring the full-featured stuff you can do with software RAID into LVM-supported commands. Just a note on the RAID capabilities, the people who've used Btrfs know this, but Btrfs also rolls in basic RAID support. It doesn't do the full range of RAID types that you can do with MD or LVM managed MD devices, but it does basic RAID 5 and 6 now, mirroring and concatenation. The Btrfs RAID code is still very new. In fact, I think to date in the upstream kernel, if you lose power, you lose the parity, which is not usually why people use RAID, is to make your data go away faster. So people are working on it. They did that intentionally, by the way. It wasn't a mistake. It was like they wanted to get the RAID format in, and then they're going to fix the persistence later. So we're working very actively on this stuff. Storage management APIs. We're trying to, if you look at the kind of wealth of storage, and I have a good slide here, maybe. We have a lot of projects that consume storage. And traditionally, what all these storage products have to do, whether it's the installer or remote management agents or things like the Overt project, they have to invoke the LVM commands or the file system commands by hand, parse the output. It's really yucky, right? So at least the parts we can control easy are, like liblvm will allow you to do programmatic APIs, C and Python bindings, to invoke LVM commands from code. Lib storage management allows you to do basic SAN management, and NetApp actually has a plugin that we've worked with and qualified as well. So the idea is to pull out something called Blivit from Anaconda, which is the storage management code, have it invoke these programmable APIs, and have everybody else use the Blivit code who wants to do either a CLI, like Storage System Manager, or a remote agent like OpenLMI. Get some commonality in here so we fix bugs and add features once. Hopefully it won't be visibly different to users, except that hopefully it'll be easier to use and more common in its capabilities. So this is kind of the fun part of the presentation. This is where I'm actually originally a local file system person, so this is where I actually enjoy talking. We are going to do full support for the first time ever at Red Hat for 3 local file systems. When I joined, it was ext3 or nothing else. It's kind of like you can have any color you want as long as it's black. So we're going to be able to do ext4, XFS, and Btrfs. Btrfs is still a little asterisk. It's assuming the wheels don't fall off before RHEL 7 comes out. We're also going to remove all restrictions on what you can use these for. You can use them as your boot partition, your system partitions, or your user data partitions. Again, some might be better tuned for certain workloads than others. Btrfs, for example, is great, I think, for desktops or maybe a box with like no hardware RAID cards, but lots of SATA drives. We want that extra data integrity that Btrfs gives you. It does check something on data and metadata blocks. The other file systems don't do that normally. ext2 and ext3 are still fully supported, but we're not going to compile in the ext2 or ext3 kernel code. This will be a little confusing because when you mount them, we'll use the ext4 driver to mount them, and you'll see ext4 as the file system type in various system things. It should be just as slow as ext2 ever was, so you should be fine, but it could be confusing. If there's, we did this in the Fedora project a couple years ago, 0 complaints. But again, it's easy to roll back. The idea is to reduce code maintenance for us, make sure we fix bugs once. It's really embarrassing to fix a bug in ext2 and forget it in ext4, and this makes us look maybe a little better sometimes. Steve already mentioned he's enthusiastic about having all 3 layout types. There is no planned support for PNFS on the server side in RHEL 7 currently. That's still an upstream kind of pipe dream. Please, yes. Yep. Let me give you the next slide. Yeah, so this is a big change. So XFS will not only not be a layered product, it'll be the default file system. So I think I'm allowed to say that means we don't charge you extra money for it. Right. So, and it's going to run on all architectures as well. So we have our XFS team running XFS and Btrfs and ext4 all on all architectures, on S390 power and working with the upstream of the ARM project. All this stuff is contingent. If you saw any other roadmap type of presentations today, you saw the big boilerplate slide. The marketing people didn't give me that, but this is all contingent on us testing and making sure that it's quality code. And we're still looking at the maximum file system size for RHEL 7, but I'm going to show you what I think I have it later, but I'll tell you, we're going to move XFS up to 500 terabytes. ext4 and Btrfs, we're aiming at 50 terabytes. I want to get them beyond 16 terabytes, which is the magic number in the kernel code. It's the number of 4K pages you can address with 32 bits. So we'll see all the bugs at 50 terabytes, but not stress them too horribly. GFS2 is going to go to 250 terabytes. That's our plan. Anybody need bigger? Nobody? Okay. For you, we'll change everything. How big do you need? A petabyte. Yeah, a petabyte's a popular number. And so what we do is we'll bump up to 500 terabytes, and then over time we'll evaluate how confident we feel in going beyond that. And again, if you have a specific workload, you can come talk to Red Hat support and our product teams, and we can see if we can get you higher, get you what you need. Is there another question? Yeah. It's hard to see. There's this light shining at us. It looks like a train's going to hit us. Yeah. Yeah. So XFS is kind of the reigning champion in the high-performance local file system space for a lot of workloads. It tends to extract the most out of hardware. Even with these PCI Express SSD cards, XFS is the one that the vendors will benchmark their own proprietary things against. It's kind of cool that way. And I will mention that a lot of people who stand up enterprise storage appliances use XFS, all the way from the low-end NAS boxes all the way up to high-end servers whose vendors I can't mention. But it's kind of neat. We also made that choice for Red Hat storage. I managed the Red Hat storage business unit engineering team for the first year. I'm a big XFS fan, so by well-reasoned logic, XFS was a requirement. Right. But it is also, for a very serious reason, it's the only file system we have in RHEL 6 that goes beyond 16 terabytes. It's really easy to knock past that number today with high-density storage. 10 plus 2 SAS, nearline SAS drives, you're pushing 30, 40 terabytes just there. Right. So ext4, I don't want to be mean to ext4. We invest a lot of work in making sure that it has enterprise features like the punch hole support and other things. We make it much faster to initialize ext4 now. There's something called lazy inode initialization in RHEL 6. It's still our default file system in RHEL 6, and it's something that a lot of people are familiar and comfortable with. I will encourage you, and when I was encouraging people to move from ext3 to ext4, move with backup. Don't convert in place. Right? If you go to Google and see somebody talking about how easy it is to migrate from ext4 to Btrfs and back again, it's true, but don't call me when it breaks. Right? We don't test it, I don't recommend it, and oftentimes you don't get the performance advantages. So again, there's things that kind of work sometimes on a good day, and things that we want production users to do. So we try to document what we think works and what we test. I would avoid ext4 for very large storage configurations. It has some basic scalability issues in the way it does files and some of the structures. You know, and again, if you really love ext4 and you're using Android, it's in your pocket. I think Google made it its default on Android handsets a year or so ago. It's also the thing underneath the user space file system that's Google's GFS. We had GFS first, though. Yeah. Btrfs. This is our new file system. If you don't know Btrfs, people often think it's a ZFS clone, which is not true. Most of the people working on Btrfs had never tried ZFS, including me. But it does do some of the same kind of things that ZFS does. It rolls in logical volume manager and snapshotting, multi-disk support, RAID support, and it also has a neat feature that you can do metadata and data checksumming. So if you get an I/O error back from the stack, it can say, hey, I know I'm a mirrored device. I can go try a different mirror, or I can try to rebuild a RAID without propagating an error up. That's kind of neat. It has extensive back references, so built into it, if you get an I/O error, it can say, not only did you get a block error at SDA offset 1,000,005, and say, by the way, that's foo.txt, right? Or that was an I/O error in my metadata. You need to run some kind of repair tool. So it hopefully was designed to give you human, meaningful errors back for when you have I/O errors, and let you as a sysadmin or as a user do something reasonable. Like, hey, I don't have to restore the whole drive. I just need to get foo.txt back for my backup. Again, one of the big things we're looking at now is where does it make sense as a use case, focus our testing on the right scale, the right kind of performance and I/O workload. Back to you, Steve.
I'm back. Some updates. RHEL 7, I used to think RHEL 7 was a 4-letter word, but now I'm actually kind of liking it because we actually do have some nice features coming up in RHEL 7. The server, Bruce Fields, he's the maintainer of the Linux NFS, and he works for us. Did an excellent job, almost single-handedly, to get 4.1. I'll go ahead again. Did I mention that NFS talk at 2:30 at room 206 yesterday? Tomorrow? Oh, did I mention that? Okay. Well, I'll go in more what this actually means. But bottom line is it's consistency. There were just two things, because with V4, we claimed that it was firewall friendly. Well, we kind of oops, because the callbacks didn't go through the firewall. They didn't use it. So that was one thing. Again, in the talk tomorrow, good. But I want to kudos to Bruce Fields for doing this. Basically, single-handedly got version 4.1 into the. Working with guys like that are just great. It's amazing. Unfortunately, not yet. Parallel NFS is not in a Linux server yet. There's places out there. There's people pushing. Tony is some people pushing for it, and we'll see. We'll see. RHEL 8, hopefully. Again, I've gone into the updates. Block layouts, we talked about this already, about the direct access to the SANs and objects in the file layout. As I said, NetApps made it happen because, well, it's the only one that they support, so it kind of worked out well for them. And so it worked out well. And so, but when we have access to the, again, with the client direct access, EMC is a big one with the blocks. They do the blocks, and then Tony does the and Panassa. Very good. That's good.
They don't like blocks, Steve. You chased them out.
Oh boy, I'm sorry. Sorry. Yeah. All right. And free beer started already? Oh, what? No, we got time. All right. This is something new. Support. I'll go over what exactly this again means. Did I mention that? The NFS talk at 2:30 at room 206? No, okay. We will go over this, but basically what this label NFS is something that's been around for a long time, and we allow to be able to secure your NFS server with label with secure SE Linux. You will be able to accept them. And some of the use cases are to have virtual VMs on your NFS server. You'll be able to secure it now. Again, I'll go more over what this actually means. And also in the talk I have, when we come to talk, I have a handout that shows everything, how to do all this technology, how to set it up. It's a line by line cut and paste. I actually use it for me when I have to go back and set things up like IPA and whatnot. So, but this is something new. It's a 4.2 thing. Again, like version 4 NFS version 4 had updates, version updates into it. And so this is a 4.2 thing. Okay. One last final thing. One thing I do talk in our talk is if you use secure NFS, I have your answer. But you got to come to the talk. I have that answer for secure. If you use secure NFS, that's something we've also done a lot of work on. So, thank you.
Yeah. Okay, we will get you out for beer time really soon. Yeah. So GFS2 again. We continue to work on GFS2. Again, it's mostly focused on performance. There's not a huge amount of new features coming in GFS2 as a product. We keep up, but the one kind of nicer thing is Red Hat's going to be working with the Performance Copilot, and GFS2 has support integrated for that. Working on faster repair time for GFS2, always important, and getting itself self-tuned to RAID stripe sizes at makefs time. So I think I mentioned most of this. The one thing I didn't mention a lot about is when you have snapshotting either with LVM or with Btrfs, we are working hard in RHEL 7 to allow you to do a rollback after something like a bad upgrade, right? So you'll be able to do that like checkpoint and a restore after a YUM update or an RHN-based update. XFS, I mentioned, I think was hardening the metadata, so we'll be able to have more assurance in detecting errors if they happen. So I'm going to jump to kind of the fun projects. As I mentioned, some of the things that we're challenged with is there's a lot of instructions in the I/O stack today when you drive I/Os down the stack. What we've done effectively is cut away SCSI for most of the PCI Express cards. A lot of the traditional stack was left on the floor. Well, the SCSI Standards Committee, a committee called T10, has been working to get a streamlined version of SCSI called SBC4. But we focus just on disk technology storage. It won't work with your CD changer or your jukebox or your printer. I think SCSI even does printers somewhere, or tape devices. There's also support in SCSI for an atomic write command, an all or nothing write. You kind of assume an atomic write for SCSI at 5 12-byte sectors. It may or may not be true, but they're trying to put real teeth in the atomic write. Some new devices like Fusion I/O has support for an atomic write today with some of their advanced products. This is something we've worked on a long time in the Linux community. The ability to tell a storage array, like a filer or a SCSI array or a file system, I want to make a copy of file A or part of file A, and I want to put it over in file B, and not bring all the bytes over the wire and send them back down again. This is something that we actually had a proposal for like 4 years ago, and I think the upstream community dissolved into an argument about the name of the system call. And kind of, I mean, that's my remembering. So instead of something normal, we have a new name. Zach Brown works for Red Hat, works on Btrfs mostly, but Zach has implemented and pushed patches for something called copy range. It takes 2 file descriptors and a ranged write. The file has to exist as a target, but it doesn't have to be allocated. So, and we're also going to plumb this into the SCSI stack, the storage stack, to device mapper, and to NFS, and local file systems that support something like RefLink, like OCFS2 or Btrfs. There's an article here and also a pointer to the posting. If you have interest or have an opinion about, the arguments or the name of the system call, please don't complain about the name. Arguments are good. Yeah. Another thing we're trying to do is get more intelligence down the stack. Applications often know, for example, that I'm a backup app. I'm going to write the data once, don't cache it. There's no way really to tag the I/O today. We've had a lot of proposals over the years, again, through standards committees. I think Seagate proposed a standard with a very rich set of hints that the device manufacturers wanted. The body voted it down, I think, as too complicated and too kind of hard to implement. So in the Linux file system and storage world, we're probably most likely going to take a few basic hint types, give you hooks at fadvise, and pass those down the stack. Things like, please do cache this is important. You know, this is right, it's a backup data, don't consume my precious DRAM. Some people ask for boot support, you know, but again, pick a few common things, don't pick dozens of things. Does fadvise sound like a good way to go? Anybody have a better system call? Yeah. We also talked a lot about how to improve error codes back up the stack. This is probably more in the developer layer, but we file system people complain a lot about the block people not telling us much other than, oh, the I/O didn't work, right? Oftentimes you know more than that in the context of the I/O stack. We want to know whether it's a temporary error, whether it's something that we might be able to retry. And the I/O layer isn't just SCSI. It can also be like software targets like Device Mapper. If Device Mapper could tell us, hey, you got a bad bit of data, but you know, it's mirrored, you know, I might be able to rebuild it. So again, this is something we hope to get into the stack to give us a richer ability to have more meaningful errors propagated back up and logged to users as well. So there's a lot of talks. I think Steve mentioned once or twice there's an NFS talk tomorrow. We also have a panel tomorrow where we have CTO level people from Tonian, NetApp, Panasys, and EMC coming to talk about PNFS and their products and their vendors. I welcome that. And you know, with that, I'm happy to take any questions. Please do feel free to ask anything you want.
So the copy on range.
Yeah. Give me
The copy on range, in the case of an NFS, will that NFS server, will that mean if I do a copy in the client, the server will take care of it for me and not have to go round trip?
Yes, it's part of the 4.2 spec. Yeah, service, I'll talk about that in talk, but yeah, but that is the theory.
Right on.
Yeah, so you send the system call over and a range, and the bytes don't come over the wire at all. It's incredibly important for things like virtual machine images, really big files, right? That's yeah, big files are good. Other questions? Question down there?
Give me a second here. Here you go.
How do you stack that up with Gluster?
Go ahead.
Your parallel NFS, you guys ever compare that and the throughput with Gluster?
Not yet.
No.
The answer is, oh, watch out. I'm going to tweak here. Not yet, no. But parallel, it's two different things, though. It basically is, with Gluster, you don't have the parallelism. You don't have the access to all of the disks, if you will. So
yeah, I'll jump in and say, I mean, with PNFS, you could implement PNFS on top of Gluster. The Gluster team doesn't have PNFS plans today, and they only do NFS v3. But they do have a native Gluster client you can install, which is multi-server aware, so it gives you kind of the same flavor as NFS, but you have to install software, like libgf API or the Fuse base code can do that today. But I think there will be different use cases. PNFS can allow like really good transactional storage. I think you could do databases on it with enterprise arrays. Gluster is not well tuned to random I/O workloads.
Rick, you talked about integrating XFS and all that kind of stuff. Is there any talk at all about using the clustering extensions to XFS that were inherent in its design?
Yeah, so the CXFS bits, I believe, are still not open source. I don't believe, are they out in the Linux? They're not in the upstream kernel.
I don't know if they've been in the upstream kernel.
Yeah,
I don't know if they've been in the upstream kernel.
SGI has a clustered XFS extension, which I don't believe has been pushed out. Personally, I think we have two clustered shared disk file systems. We have OCFS2 in the community and GFS2. I'm not sure that we need a third, but yeah. Question?
So with user and caching of metadata information of the disk and its attributes, one of the problems that could come is if there's a small SAN event, maybe a temporary outage, the system scan up could take a huge amount of time, and that makes your application go really bad at that point of time. So do we plan to make UDEV just scan a particular section of SAN or something like that?
Yeah, I don't know the details. Ewan, we have one of our SCSI guys here who put on the spot. I don't know how the scan mechanism works.
Yeah, are you talking about from system booting or while it's running?
Either at the launch or intermittent outages.
So there's some investigation going on right now about a particular type of SAN failure that you don't get an RSCN back on the host bus adapter. So we're looking at some changes to the air handling to improve that. We're not looking at anything specifically with UDEV for scanning, though.
Yeah.
Thanks.
It appears really popular. A question in the back? Yeah.
The move to including XFS in the default file system in RHEL 7, is there any consideration for making it a non-purchased supported product on RHEL 6?
Yeah, that's more of a business question. I think the intention is to still have it as an add-on in RHEL 5 and RHEL 6. So think of it as an enticement to jump forward. If you're an XFS user.
Is that it?
No, there's one over here. You can just yell it out.
Yeah, this actually happened with a different platform. They were trying bid provisioning with NASBox.
Yeah.
And they had this funny thing. If it actually ran out of space, it would take the volume offline, which made the database software that was using it very unhappy.
Yeah, so
Coming up with a different code that tells that database software this is what happened.
yeah, so that's a little bit of what I was referring to, probably not very specifically, but the thin provisioning alerts are what lets you, there's high water and low water marks. So as you trip over these thresholds, most file systems, by the way, do really poorly when they run out of space. When they think they have space and you all of a sudden start throwing I/O errors. So that ties into both of the proper alerting up the file system stack, sending a user alert to the sysadmin saying, hey, provision more real storage, and also giving the right code back to the file system saying, it's not really an I/O error, it's an out of space thin error.
In this case, the file system was on the appliance line.
Well, that would be a vendor specific issue.
Yeah, I think, well, if NFS could send up a different code, told it, hey, your thin provisioning's out of space. Not, you gave it a fatal error instead of telling it, hey, your thin provision, you don't have to die, but you can't use that.
Right. Usually there are very specific error codes that get sent, but they might not be sent in band. But you'd have to talk to the vendor about their, you know.
It has to be a standard, so you guys would have to, somebody who can get into the standard would have to say, hey guys, this standard
Right.
has to change.
Yeah.
Anybody else? Oh, good. Thank you for coming.
Thank you.